Hi everyone and welcome back to my channel. In this video, I want to show you how to calculate the PMV and PPD in compliance with the ASHRAE 55 2020 and the ISO 7730 2005. This video is a new take on a video that I previously released on how to calculate the PMV index in compliance with these two standards, because many things have changed since then. First of all, a new version of the ASHRAE 55 was released in 2020. Secondly, we have updated the Pi Thermal Comfort package, which is now in version 2.01 at the time of recording this video, which is April 2022. If you're going to watch this video in the future, always check the version of Pi Thermal Comfort on our official documentation here, because it is extremely important that you always reference the latest version of the documentation, just in case we release new updates or we fix some issues. You can check our documentation or read the docs and then look for Pi Thermal Comfort. This is going to be the website, and then here you can see the latest version that was released of the package. In this video, we're going to talk specifically about the PMV PPD model. I'm going to show you how the ISO and ASHRAE model compare, how to calculate them, and how to calculate the PMV over a batch file which contains several inputs. We have introduced some new changes which makes the code much faster, so you can run like more than 10,000 calculation in just a few seconds. Before we start, I just want to explain what is the PMV and what is the PPD. If you want to find out more, I will always suggest you to go back to the relevant standard or to read more in the ASHRAE fundamentals. But basically, the PMV stands for predicted mean vote, while PPD stands for predicted percentage of dissatisfied. The predicted mean vote is the average thermal sensation of a large group of people sharing the same environment. I know this definition may not be 100% clear, because what does a large group of individuals means? But well, this is the definition that has been defined by Fanger, who originally developed the model in 1970. And then this model throughout the year changed a bit, because we have the original Fanger model that is still used in its current form in the ISO 7730. Then we have the PMV model, which is calculated in compliance with the ASHRAE 55 2020, which does the calculation in a slightly different way. We have a paper, by the way, on this topic, which you might find relevant, which will allow you to better choose which of the two formulations to use. In summary, we found out that the ASHRAE version of the PMV is slightly more accurate than the ISO version. So, if you're free to choose whichever model you want, we would recommend to use the ASHRAE 55 version. We are working on a new paper in which we are going to compare more formulations of the PMV model. But since the two main use standards in the world use these two formulations here, at this point in time, it is possibly better to use the ASHRAE 55 formulation. How these two models differ? Well, the difference between the two models is that the underlying code is the same to calculate the PMV. The main difference is that the ASHRAE, to better account for elevated airspeed, first calculate the cooling effect using the input parameter that you pass to the model. Then this cooling effect is subtracted from both the air and the mean radiant temperature. And since we have already accounted for the air movement, then we pass into the input of the PMV model air velocity equal to 0.1. Of course, you don't have to worry about all this if you just want to use Pi Thermal Comfort, because all the calculations are performed in the back end. But I just want to explain which are the differences so you can make a better informed choice on which model is more appropriate to use. Of course, the two models differ only if the airspeed is above 0.1 meters per second. In our paper, as previously also shown by other researchers, we also showed that the PMV model is only accurate within a very close narrow range of thermal sensation. And in particular, we showed that the model is only accurate in predicting people who reported to be neutral, and then eventually the accuracy slightly degrades or decreases when trying to predicting people feeling slightly cool or slightly warm, and then the accuracy is extremely low when predicting people feeling cold, cool, warm, or hot. Another important thing to keep in mind is that the ISO standard says that you should only use the PMV between -2 and +2, which is a thing that very few people do. So now that I've explained the main differences between the two models, I think it's time to quickly explain which are the 6 inputs that you need to pass to the heat balance model, which is basically the PMV, and then we're going to see how we can calculate the PMV and PPD using PyThermal Comfort. The first variable that you need to pass into the PMV is the dry bulb temperature. You can pass it both in SI unit or in imperial unit. I'm going to be referring mostly only to SI units because are widely used across the board. The second parameter that you have to pass is the mean radiant temperature. Usually we don't measure the mean radiant temperature directly, but we usually in an environment measure the air temperature, air speed, and globe temperature. There is a function inside PyThermal Comfort that allows you to calculate the mean radiant temperature from the globe temperature, air speed, and air temperature. So check that function. So that function here inside the psychrometric function basically allows you to calculate, as I previously mentioned, the mean radiant temperature from the globe temperature, dry bulb temperature, and air speed. If you want, you can also pass the diameter of the black globe sensor and the emissivity. The relative airspeed, which is the third parameter that we have to pass as an input to the PMV model, is actually not the measured airspeed. The measured airspeed is usually measured at 3 different heights based on the body position of the participant. If the person is standing, for instance, we have to measure the airspeed at 0.1 meter of height, 1.1 and 1.7. We then average these 3 values. But this is not the value that we need to pass inside the PMV. The value that we need to pass into the PMV is also affected by the metabolic rate. Why this is important? Because as the person moves and it has a high metabolic rate, we are expecting that he or she is moving his limbs. And then consequently, this generated a self-generated airspeed. Therefore, we need to use the function that is provided in PyThermal Comfort to calculate the relative airspeed. Okay? You just have to pass the velocity that you measure and the metabolic rate. And this function is going to calculate the relative airspeed for you. But it's important that you do so in order to perform a right calculation. Then we just have to pass the relative humidity. This should be self-explanatory. The metabolic rate. Again, you just have to estimate the metabolic rate by observing the participant. Or if, on the other hand, you are designing an environment, you can just look from the list of metabolic rates and pick the value that closely match the occupancy that space is going to have. Then we have to pass the clothing insulation. Be aware that as for the relative airspeed, also the clothing insulation is affected by the metabolic rate. Here the effect is kind of opposite from the relative airspeed, because the more the person is moving, the more air will most likely go under his clothes. So will kind of reduce the thermal insulation of the clothes. So while higher metabolic rate generate a higher airspeed, and consequently there is more cooling through convection, at the same time we have that the more the person is moving, the lower the clothing value is. Okay, so these two values are very important to take into consideration. For low value of MET, you will not see many differences, but later on in the example I will show you that as the value of MET increases, then the difference becomes more and more significant. Finally, you can pass inside the PNV the external work. Of course, if a person is lifting up a box, you should also take into account that is actually performing work. So part of the energy is actually converted in potential energy of the box. So technically, you should also take into account the external work. However, generally is set equal to 0, but you should take into account. This is also in unit of MET, as the metabolic rate. Another parameter that we need to pass to the PNV is the standard. At the moment, we have only two models which we can get, so is the ISO and the ASHRAE. In the future, we may be adding new PNV formulations, but at the moment we only have these two here. And I've already explained before what is the difference between the two models. Finally, you have to pass the units and limit inputs. Limit inputs is a very important variable that we just have added to version 2 of PyThermal Comfort. By default, PyThermal Comfort will return values only if you are within the standard applicability limit. If you are outside the standard applicability limit, we will return a NA, or more precisely, we are going to return a NumPy NP none. We decided to do that because we really want to make sure that you use the standard only within its applicability limits. Because if you use it beyond where it was designed to be used, then you're going to get results that are not consistent and might not be even accurate. Already the PNV is not very accurate within its applicability limits if the person is not neutral, not thermally neutral. Plus, if you start using the PNV outside this range, then you're going to get results that, yes, are a number, but then eventually this number has no meaning. Consequently, by default, we're going to be returned NA if you are outside the applicability limits. If you want to find out more, which are the applicability limits, you can find here a list of the limits. Please note that if you really want to, you can set this limit input to false, and then you're going to get a value, no matter of what your input is. However, just do that if you are really sure of what you're doing. So let's move to PyCharm. I'm going to show you a quick example on how to calculate the PNV with the PyThermal Comfort. So the first thing that we need to do is to install the latest version of PyThermal Comfort. I have already PyThermal Comfort installed on my computer. So in my case, I'm going to do in the terminal that you can see here at the bottom of my screen, pip install PyThermal Comfort -- upgrade. This is going to upgrade PyThermal Comfort to the latest version, which at this time is version 2.01. As you can see, it was successfully installed and now we are good to go. The first thing that we will need to do is to import the PNV function. So here in PyCharm, I can run line by line by pressing Shift Alt E and just follow along with me. And here at the bottom, you will see the output of my commands. Then we import, as I mentioned before, the vrelative and the ClowDynamic function. We're going to import also two dictionaries that you may find very useful. One is the MET typical task and the other one is Clow of individual garments. I'm going to run these imports and I will show you the MET of typical task and I'm going to show you the Clow individual garments. So let me import pprint. So I'm going to be able to run pprint, which is pretty print of MET task. Here inside this dictionary, you can find the metabolic rate of a lot of different type of activities, which you may find useful. Okay, if for instance, as I previously mentioned, you want to design your building for a specific type of activity, or if you are conducting a research and you are observing the activity level of some participant. Let's say that your participant is reading seated, then it's going to have a metabolic rate of 1.0. The same is true for Clow of individual garments. We have the clothing insulation of a list of individual garments. We are going to set up the input variables, so the dry bulb air temperature, mean radiant temperature, air velocity, which as I previously mentioned is the average air speed at 3 different heights. Then we have the relative humidity, followed by the activity, which in this case is typing, because we don't want to pass a value. Of course, later on in the PMV, you will have to pass a value. And then we have the garments that the person was wearing while we were asking him or her to complete the right here, right now survey. So let's run these lines, and now we have set up these variables. What we need to do is to calculate the MET. How we can do that? We can use the dictionary that I showed you before, and then we're going to see that for a person that is typing, we have a metabolic rate that is 1.1. The same, we can use a comprehension list here, and then calculate the sum of all the individual garments and calculate the total clothing insulation. So I'm going to run this line here. So I'm going to run this line here, and then we're going to have MET that is equal to 1.1 and total clothing insulation, which is equal to 0.38. We have to calculate the relative airspeed and the flow dynamic, which you can use the function provided in SciPy thermal comfort. So we can run these two values here. And let me show you the value. So VR is now 0.33, despite we measure an air velocity of 0.3. The difference is due to the metabolic rate. In this case, the metabolic rate, since is lower than 1.2, and we're using the ASHRAE 55 method to calculate the flow dynamic, this will not affect the clothing because the metabolic rate is lower than 1.2, and consequently the value that we measured before and the new value are going to be the same. Of course, if I change the metabolic rate to 2, then you will see that the clothing dynamic decreases. Okay, so from 0.38 to 0.304. So let's go back, and now we just have to run this function, which is PMV PPD. We pass the input values, we pass the standard, and then we can calculate the results. After we calculate the results, we can also print the results. So this condition will lead to a PMV which is of minus 0.55. So this group of people most likely are going to be on the slightly cooler side. Okay, we are between the neutral and the slightly cooler. Slightly cooler will be -1 and neutral will be 0. And then we can print also the results as a string if you prefer, by just running this line. If on the other end you want to use the IP system, you can just say that the unit has to be IP. So let me run this line here, and you get the results for the IP unit. Of course, the value of PMV is independent between if you're using imperial or SI units. Now you might ask, okay, you show me how to calculate with one input, but most likely you're going to have a table of inputs, okay? And you are going to have a file that contains a lot of inputs. And usually if you're using Python, you will store this value as a data frame. So let me actually do that. Let me import this file that I have here on my computer. Let me show you the data frame. So here we have a data frame that you can see here in my terminal, that we have an array of dry bulb temperature, an array of mean radiant temperature, air velocity, relative humidity, metabolic rate, and clothing. You may have collected this data, or this could be an output of an energy simulation or measure from a real building. Wherever it is from, you can just pass this value to PyThermal Comfort, because now most of the function inside PyThermal Comfort accept list or NumPy array as inputs. So let me show you how to do that. The first thing is we have to define the variables, and we can extract them from each column. So we get the dry bulb temperature column, and then we get the values. So here we get an array of values, and then we assign it to TA, or more correctly should have been TDB, because dry bulb temperature. Then, as we did before, we just have to calculate the relative airspeed and the dynamic clothing. So let's run this function, and as you can see, this time as an input we are passing two arrays, because velocity is an array and metabolic rate is an array. Be careful that these two vectors must have the same length, or alternatively one of the two could have a length equal to 1. So for instance, we can see that the metabolic rate did not vary in our building, but the velocity varied. So we can pass an array of velocity and one single value of met. But if you pass two arrays, these two arrays must have the same equal length. Okay? Let's calculate the results. So this time we pass an array as an input. We get the results. We assign, and let me show you the results, how they look like. So it's basically a dictionary where we have PMV and the value of PMV, and then we have PPD and the value of PPD. So we are going to access our data frame that we saw before. We're going to add 4 columns. One is the relative air velocity, one is the dynamic loading, and then we have PMV and PPD, because I want to show you all the results. So let me run this function here, and then let me print the head, so the first 5 rows of our database. Here you can see all the results. Of course, if you just would have printed the whole database, you would have got all the results. But basically now we have the relative airspeed, which is equal to the airspeed if the metabolic rate is equal to 1. But as the metabolic rate increases, as you can see here in this column, the more the relative airspeed increases as well. On the other end, the opposite is true for the dynamic loading. So the more the metabolic rate increases, the more the dynamic loading actually decreases. And these are the two values that we use as an input to the PMV model. And here are all the values of the PMV model. And here are all the values of the PPD, which is the predicted percentage of dissatisfied people. Of course, even if you have a PMV equal to 0, which here in this case we just have this one that is equal to close to 0, we can see that we can never reach a predicted percentage of dissatisfied which is also equal to 0. So there will always be someone in the room or in the space that is dissatisfied with the thermal environment. That's kind of a fact that we cannot do anything about. One very important thing that I would like to show you is the change in behavior of pythermal comfort. Before, if you were happening to enter an input variable that was outside the standard applicability limit, you were just getting a value error or something here in the Python console telling you that your limit was outside applicability limit. We believe that that was not sufficient, and also based on our requirements that you had to have to improve the code speed, we decided to change that. Now, if you actually pass a value that is outside the standard applicability limits, you're going to get a results that is an NA array. Okay, so as you can see here, I've passed the inputs. The other inputs are all fine because before we saw that everything was fine. But now I'm passing a dry bulb air temperature which is 45 degrees. And then I'm assuming that that stays constant throughout all the different entries. That's why I can only pass one array that is only length of 1. But as you can see, the very important thing is that the results that we're getting are NA because we are outside the standard applicability limits. One thing to change this behavior is to pass, as you can see here from the documentation of the function, you can say limit inputs, and then you can say false. In this case, we are going to get a PM value no matter of the fact that we are outside the standard applicability limit. But as I mentioned before, please try to avoid using this functionality because you are outside the model applicability limits and what you are getting are numbers, but they mean very little because the model was not developed collecting data in those temperature ranges. So you still get a value, but that value may not be accurate. So the last thing that I want to show you is the improvement that we have done in the back end. So you can see how fast is pythermal comfort. So I'm just generating here an array of 10,000 entries with dry bulb temperature. I'm then assigning a value of 25. Doesn't really matter that. I just want to show you the speed of pythermal comfort. And you can see this is an array of 10,000 entries. I also have the metabolic rate. I calculate the V relative and flow dynamic, and you will see that the calculation is practically done in no time. And then here I time the function. So to run 10,000 calculations is going to take only a few seconds. And this is going to take a few seconds if you use the ASHRAE model. Because the ASHRAE model, as I previously mentioned, it takes more time because every time we have to calculate the cooling effect, which require us to do the calculation of the SET temperature. So it's very intensive. So it took approximately 7 seconds. If on the other end we do the calculation in compliance with the ISO model, you will see that the calculation takes only 100th of a second. I really hope you find this video informative. If you did, please consider liking the video and subscribing to my channel. If you have any question, please feel free to write a comment down in the video section below. If you have any comments about our package, or you spot any issues, or you want us to add new features to PyThermal Comfort, please open an issue on GitHub and we're going to be able to reply over there and address your issues or comment. Thank you very much for listening and see you in the next video.